because they have extraordinary electrical and dielectric properties, and my talk is devoted to the connection between glassy dynamics and charge transport in these systems, and not only low molecular weight, but also polymeric ionic liquids are available nowadays. The talk, next few graph, this does not, okay. I have organized my talk in several sections. Briefly, I will speak about the relationship, what glasses are and what is their dynamics. And I realized that in this conference, mainly solid state materials are in the focus, while I will speak here about glasses, soft glasses, which are typically realized in soft matter systems like polymers, but also liquids and elastomers and so on. Briefly, very briefly, I will speak about broadband dielectric spectroscopy. I will introduce to you ionic liquids, and then I will speak in detail about the interrelationship between glassy dynamics and charge transport. And a bit later, I will speak about the low molecular weight and polymeric ionic liquids and the comparison about this. So what are glasses? And now I have to ask for your understanding. While originally this talk, this few graph had several animations, but the animations didn't work. So you see now a screen which is a little bit overloaded. If you have a liquid, then either you can have simply crystallization, and then a long-range order is realized. If you have in the liquid state, you have no long-range order, but you can cool this liquid to the glassy state, and in the glassy state, one has no long-range order. And if you plot, for instance, volume versus temperature at different cooling rates, then you observe that there are two kinks which indicate the so-called glass transition. And you realize in such an experiment that this temperature, which is indicated as glass transition temperature G1 and G2, that this temperature depends on the cooling rate, and this means that the glass transition is not a phase transition in the sense of solid state physics, but unfortunately, while this nomenclature glass transition is simply the worldwide nomenclature, and this cannot be easily changed. Yeah. Now let's make a Gedanken experiment. If you, again, this was nicely arranged with animations, but they do not work in the moment. If you just consider an isolated molecule in a zeolitic cage, then you can directly, and this can be nowadays realized, for instance, ethylene propylene glycol in zeolitic cages. And then if you measure the relaxation time versus temperature, then one observes simply an Arrhenius type temperature dependence as indicated in here. This is a situation for a single molecule relaxation. The situation in a liquid is completely different. Yeah, if you consider this primitive sketch of glass, yeah, just in 2D representation, and if you consider, for instance, here a molecule in the middle surrounded by surrounding molecules, then you see a potential landscape which is very complicated, and this is also a potential landscape with continuously changes, and even with modern computer possibilities, it was up till now not possible to describe this potential landscape on an atomistic scale. Experimentally, it is since decades, since more than 100 years, known that there is this so-called Vogel-Fulcher-Tammann temperature dependence, which is indicated in here. And this means that the activation energy for this glassy dynamics relaxation, changes continuously with temperature. And a possible explanation to describe this is the fact that the length scale on which the relaxation processes take place increases with decreasing temperature. So typically one has here at the calorimetric glass transition temperature a length scale of about a nanometer or perhaps 2 nanometers. Depends, of course, on the molecular system one is analyzing. And why does it now not work? Yeah, we had this. Yeah, and well, if you ask a chemist concerning the glass transition, then he says, well, I measure the glass transition with calorimetric techniques. In a calorimetric technique, you measure the heat capacity versus temperature, and then in a glassy system, you observe such a step. And this step is indicated, and the turning point indicates the glass transition temperature. But as said, this so determined glass transition temperature depends on the cooling rate. But as a rule of thumb, at a relaxation rate of 10 to the minus 2 hertz, one is arrived at a temperature which is identical to the so determined calorimetric glass transition temperature. Another way, of course, to determine glassy dynamics is simply broadband dielectric spectroscopy. And there you measure a relaxation process as it is shifted through the spectral window. This is now just a very limited range. Usually you can extend the spectral range from 10 to the minus 4 hertz up to 10 to the 9 hertz. So one can measure easily 13 decades. And the mean relaxation rate versus inverse temperature is now indicated here by this so-called Vogel-Fulcher-Tammann dependence. Yeah, and now, so let me summarize the findings for glassy systems. Well, typically the calorimetric and the dynamic glass transition, they are interlinked, and by the empirical Vogel-Fulcher-Tammann relationship, there are manifold ways to measure the dynamic glass transition or glassy dynamics, which is identical. Yeah, you can use, of course, calorimetry, but also scattering techniques, of course, also more molecular techniques like dielectric spectroscopy or NMR spectroscopy. And if you ask what is the molecular assignment of these processes, then the answer is the following. One has here relaxations between structural substates, and what we observe is a continuous slowing down of the molecular dynamics according to this empirical Vogel-Fulcher-Tammann dependence. So now I need the next view graph. Yeah, now very briefly I will speak about broadband dielectric spectroscopy, but, okay. Well, in principle, we have linear material equations between the dielectric displacement and the external electric field, and this is here for the magnetic case, which doesn't play here an important role. And I will speak here about experiments where such linear material equations are valid. And well, if you ask, if you check with one of Maxwell's equations, then you find there is an equivalence between the temperature dependence of the dielectric displacement and the current density. And if you insert here these linear material equations, this is Ohm's law in microscopic form, then you arrive here at a relationship between the complex conductivity and the complex dielectric function. And well, now a typical experiment, this is propylene glycol measured from 10 to the -2 up to 10 to the 6 Hertz. We see here charts at different temperatures. This is the conductivity contribution. And here, these charts where we have this maximum, this reflects relaxation processes due to orientational polarization. And the information content which one can extract from these spectra is, first of all, of course, the relaxation time, which is given by this maximum, the relaxation time distribution, but as well the dielectric strength, which corresponds to the area under such a relaxation function. And while here a typical example of propylene, of glassy dynamics, this is propylene glycol, and as measured in a spectral range from nearly 10 to the 10 Hertz down to 10 to the -2 Hertz. And this is the typical Vogel-Folcher-Tammann dependence, but this is a completely empirical description and nothing else. Yeah, so let me summarize this briefly. Well, BDS in the modern form covers 15 decades in frequency from the terahertz range below millihertz. This is now easily available due to one of Maxwell's equations. The complex dielectric function and the complex conductivity are directly interrelated to each other. One can, with special nanostructured capacitors, one can reduce the sample amount required for a dielectric measurement down to that of isolated molecules. And we realized this is a speciality which enables especially novel experiments if you are interested in the dynamics of molecules, for instance, close to interfaces. If you have systems which are characterized primarily by mobile charge carriers, then you can directly extract the hopping time of these charge carriers. I will give you examples. If you have dielectric spectra, then you measure primarily the fluctuations of permanent molecular dipoles. And of course, you measure also the temperature dependence of the relaxation rate and the relaxation time distribution function as well. Okay. If you want to know more, then there are now several books available, and there's also a book edited by Marian Palloch from the University of Silesia about dielectric properties of ionic liquids. I will come back to this in a few moments. What are ionic liquids and why they are of special interest? Ionic liquids are salts between a large organic cation and a small anion. And this imbalance in the structure means that these materials form glasses, and they have typically a very low glass transition temperature. For instance, for this ionic liquid, as described here, you have a glass transition temperature at 220 K. You have quite high conductivity, typically 10 to the -3 Siemens per centimeter at room temperature. One has a low conductivity at low temperatures, low viscosity, and of course, these ionic liquids form a novel solvent, but they can also, due to the high conductivity, they can be used in fuel cells, but also in lightweight batteries, and so on. And what are the dielectric properties of ionic liquid in general? This is now a plot, where we have here epsilon prime, here we have epsilon double prime, and here we have, for the same ionic liquid, we have here the real part of the conductivity, and here's the imaginary part of the conductivity. And what we see now, I start from the high frequency range, at very at very high frequencies and low temperatures. The temperatures are indicated in here. We see dielectric relaxation processes, but then if we increase temperature, then immediately charge transport and conductivity is dominating. And if we increase the temperature further, then we observe on the low frequency side the dominance of electrode polarization. If you transfer the identical data into conductivity, then you observe here such a dependence as indicated here with the plateau. This plateau represents the so-called DC conductivity, but this DC conductivity is, of course, not the conductivity at direct current. It is this DC conductivity, this plateau is dependent on temperature, as you see here. And the decline we observe here, this is due to electrode polarization. And this hinders, of course, strongly charge transport. Therefore, we observe here this decline. If you transfer the identical data into sigma double prime, then we observe here charts which have this characteristic. And if one is interested in electrode polarization, which plays an important role nowadays for low weight supercapacitors, then this spectral range and this representation is of special importance. And if we now, let me just summarize this. Well, the dielectric properties of ionic liquids are given by the superposition of electrode polarization on the low frequency side and at elevated temperatures, and then by charge transport, but also by molecular relaxation processes. And all these different contributions have a characteristic frequency and temperature dependence. Okay, and now I would like to switch over to the really important question: what is the interrelationship between glassy dynamics and charge transport? And for that we need a few basic equations, and we will need, as you will see in a moment, we have to combine different experimental techniques. We need as basic equations, we need Stokes-Einstein relation, which defines a relation between the diffusion coefficient and the molecular friction coefficient. We need this relation, which makes a relation between the viscosity and the structural relaxation time, tau eta. This is also known as Maxwell's relation. We need a little bit later also Einstein's Molokhovsky relation, which makes a relation which describes a relation between the diffusion coefficient and the characteristic diffusion rate and the characteristic diffusion length. And well, this is just a definition from basic electrodynamics. This is the conductivity, mu is the mobility, n is the number density of charge carriers, and q is just the elementary charge. And if we use these basic equations, and if we combine these basic equations, then we can formulate predictions. We did nothing else than to combine relations between the equations I just showed in the previous few graphs. And one prediction is, for instance, that omega c, this is the characteristic diffusion rate, and the structural relaxation rate, they are interlinked by a constant of proportionality, which is given here by this equation. And while all these quantities are more or less quite well known, additionally, we can formulate a prediction between the diffusion rate and the molecular, the hopping rate, or the characteristic diffusion rate omega C. And of course, there is also the Barton-Nakayima-Newikawa BNN relationship between the conductivity and omega C. And it's immediately clear that in order to check these equations, we have to combine quite different methods. For instance, in order to measure omega eta, we need viscosity measurements. In order to measure the mass diffusion coefficients, we need a special NMR technique. This is pulsed field gradient NMR technique. And of course, in order to measure the conductivity and omega C, the hopping rate, we need broadband dielectric spectroscopy. And now I will focus on the first equation. Yeah, this is this relationship, and I just repeat this. This is an important prediction. Yeah, omega C is the characteristic diffusion rate, and omega eta is a structural relaxation rate as measured with mechanical spectroscopy. And this is just the constant of proportionality. And while here we have, for instance, Stokes hydrodynamic radius, and we have here for lambda a characteristic diffusion length. I will come back to these numbers a bit later. And now let's start with the first measurement. This is now a measurement of an ionic liquid. This is sigma prime versus frequency at different temperatures, as indicated in here. And we observe here first plateau, but with increasing temperature, we observe also that electrode polarization becomes dominating. But still, we have, of course, here this plateau describing sigma C DC conductivity. But additionally, we observe here a special frequency, omega C, where the transition into a power law dependence is observed. And if you analyze this in detail, then you can apply the random barrier model, which was especially worked out in the group of Professor Jeppe Dürre in Aarhus. And the fits based on his theoretical approach, which is based on the random barrier model, these fits are described here in the corresponding temperatures as these solid lines. So by you carrying out such fits, we can directly extract the time tau C. And what is the interpretation of this time tau C? This is the time within the random barrier model. And this, the random barrier model is just describes hopping conduction in a spatially randomly varying energy landscape. And this time tau C or tau E, this is the characteristic time related to the attempt frequency to overcome the barrier which is determining for the DC conductivity. Yeah, or in shorter words, this is at the end the hopping time of the charge carriers in the spatially randomly varying energy landscape. And if we now show, now I'm really sorry that this is so smashed. With animation, it would be super clear. So we have here on the left-hand side, we have viscosity, or the inverse of viscosity, versus the inverse temperature. On the right-hand side, we have conductivity. And if we rescale this with respect to the glass transition temperature, then we get two parallel charts. This is now a bit, this is difficult for you to see. And we checked this for about 50 different ionic liquids, and we observed always the same. I hope in the next few graphs this is much better to see. Here, this is now a few graph where we have combined omega C. This is the hopping rate as measured by dielectric spectroscopy. This is omega eta. This is the mechanical relaxation rate as measured by viscosity. And the dielectric measurements are, of course, broadband in a huge spectral range. in contrast to the viscosity measurements, which are restricted only to a small spectral range because of experimental reasons. But you observe here nicely that there is quantitative agreement within certain experimental margins of uncertainty, and the relationship between the hopping rate and the rate of mechanical relaxations is directly here fulfilled with these measurements. And again, we checked, and this constant of proportionality, well, has to be about 1. And well, the constants which are involved are shown in here. G infinity is given by this expression. This can be measured. And for the diffusion length or the hopping length, if you want, one has to make an assumption, and we made the assumption of 2 angstroms. And for the extension of the molecular unit, we made also the diameter. We made the assumption again also of an angstrom. But we varied, by the way, also this for different ionic liquids, and there was always very, very good agreement. And now we can do the following. We can also rewrite this in the following way. We have here a relationship between the hopping rate and here the mechanical relaxation rate. And you see there is this proportionality is realized in a huge range of time scales. And this value of 1 for this factor of proportionality is very well fulfilled. Okay, now to summarize this, the prediction number 1 is now fulfilled, and now I will switch over to prediction number 2. In order to check this, we have to combine NMR, and we have to combine diffusion measurements by NMR, and this can be only realized with pulsed field gradient NMR and dielectric spectroscopy. And the measurement is shown in here. This is now the diffusion rate versus inverse temperature, and with the open symbols describe the NMR measurements, where we measure the mass diffusion coefficient. This is very important. In the dielectric measurement, we measure the hopping we measure essentially the conductivity, but this conductivity can be recalculated into a diffusion coefficient, and then we observe the diffusion of dielectric of charged entities, and we observe that there is full agreement between the NMR measurements and the dielectric measurements. And this is very remarkable because with NMR, as said, we measure mass diffusion, while we measure with dielectric measurements the diffusion of charged entities. I will come back to this point a little bit later. And now we can combine this result with the following formula. We have here the conductivity measured directly with dielectric measurements. This is just the defining equation. N is the number density of charge carriers, which of course a quantity which is strongly temperature dependent. Mu is the mobility of charge carriers. And these are just definitions. And of course, you can write this also in a way as here in the last part of this equation. And this includes here 1 over tau h. This is a hopping time. So this is at the end nothing else than the hopping rate omega e. So what we observe here between the conductivity and the hopping rate, there's a full correspondence and proportionality as predicted by the BNN relationship. But we can also we can go a step forward and we can do the following. I go one step back. We can measure with NMR, we can directly measure, well, I start another way. If you measure just conductivity, then you have always the product between the number density and the mobility of the charge carriers times the charge of your hopping entities. And so you have here a product. But if you have if you combine this with NMR measurements, then you measure for the identical sample on the one hand side the conductivity, and you measure with dielectric techniques, and you measure with NMR, you measure the diffusion coefficient, and then you have a chance to determine separately the number density of charge carriers and their temperature dependence. And this is now realized in the next view graph. Yeah, here we have the diffusivity or the diffusion coefficient, meters squared over seconds. This is the inverse temperature. And here we have the separated mobility. And this was carried out for this ionic liquid, but we did this for quite a lot of different ionic liquids. And here we combine NMR measurements, dielectric measurements, and here this is the mobility. And with this technique, we can separately extract the temperature dependence of the number density of charge carriers. Okay, and now, so let me summarize this. Well, we checked the relationship between the conductivity and omega C for a lot of different ionic liquids, and we always observed that this so-called BNN relationship is perfectly realized. So let me summarize also this finding. Yeah, by combining NMR measurements and dielectric measurements, we observe full agreement between of this prediction. And so if one, let me check. If I summarize this, well, we checked also, of course, here many more details, but because of time, I cannot show this. And in all these checks we carried out, we came to the conclusion, that the predictions based on the diffusion theory of Einstein and Smoluchowski are very well fulfilled. Okay, so let me summarize these findings. Glassy dynamics, this means at the end rotational diffusion and charge transport, this is translational diffusion, are simply given by the theory of Einstein and Smoluchowski describing Brownian dynamics. And the reason is the following. In ionic liquids, you have a glassy system, and in the dynamics in this glassy system, well, this is described by Einstein's theory of Brownian dynamics. And we checked, well, in detail, the basic relations between the molecular friction coefficient and the diffusion by combining different measurement techniques, and it was quantitatively fulfilled, and also the BNN relationship was perfectly fulfilled. So now let me briefly say a word concerning polymeric systems. Because of technical reasons, one is of course highly interested to work with polymeric systems, and we carried out comparisons where we combined, well, for low molecular systems and the identical cation and anion we used in the case of the polymeric systems. This was synthesized by Professor Stremel. And if you carry out now the measurement, then you observe the following. This is now conductivity versus inverse temperature.
You have 2 minutes left in your talk.
Pardon me? 2 minutes?
A few minutes, yeah.
Okay, yeah. Well, I skip a few, no problem. So we have here on the low, on this side, we have low molecular weight systems. So the conductivity of low molecular weight systems is orders of magnitude higher. If you just take the plane measurements, and if you compare this with the polymeric system, you have between here and here typically about 7 or more decades. But if you do now the following, if you rescale this with respect to the glass transition temperature, then you observe that even in the polymeric system, the conductivity is higher than compared to the low molecular weight system. Okay, because of time reasons, I just switch over to the summary. Yeah. So if you have polymeric systems and compare them with low molecular weight systems, in principle, the identical mechanisms of charge transport are realized, but in polymeric systems, at the end, due to the fact that the calorimetric glass transition temperature is much, much higher than compared to low molecular weight systems, one has at the end, in the polymeric systems, much lower, in absolute terms, a much lower conductivity. Yeah, and so at the end, I would like to summarize my whole talk. Well, what are glasses? Glasses, I spoke especially about organic glasses, amorphous materials, and the dynamics of which is characterized by the so-called dynamic glass transition. You can determine this dynamics with many different techniques, but the most popular technique is, of course, broadband dielectric spectroscopy. And in ionic liquids and in both low molecular weight and polymeric systems, yeah, the dynamics and the charge transport is determined by the relations which go back to Einstein, Stokes, and Smoluchowski, and they are quantitatively fulfilled, as I showed you for one example. And at the end, I would like to thank you for your attention. This is okay, and the money came from the German Science Foundation, and this was a PhD from my group, and this is Professor Stremel, and this is Professor Jian Yuan from China, who is now in Sweden. And yeah, and of course, I would like to draw your attention to this book edited by Marian Palluch, in which many, many more details about the dielectric properties of ionic liquids are described. So thank you very much for your attention.
Because it's really an overview, and this was really complete related to ionic liquids. Thank you very much. So we have no time for questions, so we have to move on with the next speaker. That's an invited talk also with Andrzej Katuziak. So I wonder if Andrew,